Alright, so now we're going to put together the next board in the series. The next board is the serial board. So we've laid out the parts by looking at the board elements. So if we go ahead and look at the board, you can see that we've got a socket for the 68B50, which is the serial I/O chip. We've got one for the inverter hex buffer, the 74HCT104. We've got one. We've actually got the chips. We've got a couple caps, decoupling caps, and a couple resistors. Let's see, is there anything missing? I think that's pretty much it. So I will start to put this together. I will stop if there's anything that needs to be pointed out. Otherwise, I'm just going to go ahead and get going and put it together. I'm going to start with the lowest components first. And it looks like we need 3 1K resistors. So understanding the codes on the capacitors, it's pretty easy. But I'm actually going to give you a link to an online calculator that shows how you just can put the number in and it will tell you what it is. Okay, the next things we want to do are the IC sockets. Make sure you've got them all there. What I do is I pinch it with my fingernail and then set it down. Before we go too far, let's just make sure all of them are there, and they are this time. No pins or there's no legs of the ICs sticking out. Everything should be making good contact. So that's it. That's how you put this one together. Not too complicated. Let's take a look at the schematic. We'll talk about it, and then we'll see if there's a way for us to test it. So let's head over to the computer. All right, so this is the serial PCB schematic, and I have moved it and added some text to try to make this easier to understand how it works. So let's start off with the simplest part, which is this 6-pin header. This is our FTDI, our USB serial interface. Hopefully you purchased the USB CDC adapter from them. That's where this plugs in. The jumper here is simply to indicate whether the power for the entire Classic II computer is coming from the USB interface or if you're going to power from another 5-volt source. I plan on setting this jumper, and on the CPU board itself not setting the 5-volt jumper there. So if we look at this, this is where, okay, so you plug in your USB CDC adapter to understand what it is, and you take the other end of it, the USB end, and you plug it into your computer, and then you pull up some kind of terminal software. PuTTY will work. You set up the proper parameters, baud rate, number of bits, all that kind of stuff. And then as you type, you can communicate with the Z80, and as the Z80 is running software, it can communicate with us. The Z80 communicates with us through what's called port I/O. And as the designer, let's say, of this architecture, you kind of have some control of where that port for input and output is going to be available in the memory space. And the Z80 does that by using certain address lines and also using certain pins on the Z80 to allow you to map where, when a certain address is requested and certain pins are set on the Z80, where that gets mapped to. And in our case, it gets mapped to the 68B50. That's probably the easiest way to understand it. It's memory mapped I/O, or what they call the port I/O. And in terms of the Z80, it basically uses address line 0 through address line A7, so 8 bits, to whenever it has an instruction like an in or an out instruction, it then uses those lower 8 bits to address some type of device that is out on the bus somewhere. And when you design the computer, you get to decide, for example, where this 68B50 is on that bus. Where is it in the address space? Now, the gentleman who designed this kit for us already made that decision. But we can even calculate where it is by looking at the schematic. So before we do that, though, again, this is the driver chip. And you can see RX up here, TX up here, the SYN request line here. And we've also got an interrupt that can be generated. Real quick, an interrupt. That is this chip telling the Z80, hey, stop what you're doing as soon as you've completed the last instruction you're on, and I've got something you need to look at. Okay, so let's go over to a handout and let's look at some of these interfaces. Like, let's see here. We've got write here. We've got interrupt, which I kind of mentioned. We have IORQ going into the enable of this chip. And let's see, we have M1 over here. So there's a handout I found that I thought was really nice. And it discusses what each of these is. So IORQ is the input-output request. So it's active low. When that line goes low, there is an input or output instruction, a request, like the commands in and the command out, being requested. So that's an indicator that all of those things on those port addresses need to kind of pay attention for a second to see if it's their address. M1 tells us it's active low, tells us that indicates that a current machine cycle is the opcode fetch cycle. So tells us the CPU is fetching an instruction. So we probably don't, we want that to be, if it's active low, we want it to be high, meaning that we're not getting the instruction. We've already gotten the instruction. That's what set IORQ high. If we go over here, we see that the write line and the read lines, that means we're either writing to memory or reading from memory, right? And our port needs to know which is happening. Are we doing a transmit or a receive? That's how that's going to get mapped. And then we, let's see, memory request. I think that was it. The interrupt, I pointed out, an interrupt request. Interrupt request is generated by I/O devices. So they're actually sending our chip, our 68B50 is sending an interrupt to the processor. The CPU honors the request at the end of the current instruction. If the internal software controlled interrupt enable is on. Okay. So if we look at the actual 68B50, we now see that there's a number of chip selects. And we see that CS0 is tied to M1. So when it's fetching an instruction, it's low. So when it's not fetching an instruction, it goes high. So that's good. Let's see here. CS1 has to go high up. That means that we have to have a high on address 7, which is we see down here. This is the address bus. I'm trying to build it out. And CS2, that's tied to something. Let's see here. CS2 must be low. So that means that we have to have a 0 at A6. Okay. So this is what we need to kind of make some of that happen. And we need the M1, as we just indicated, not getting an instruction. Okay. So that means all of these could be set to do the thing, right? Do what we want. So now let's take a look. What else do we have? A0 is tied to RS. RS is the register select on the serial chip. What does it do? If it's high, we're looking at transmit and receive data registers right here. These are the data registers. That means if it's high, we can transmit or receive off of it. And if it's low, we're looking at control register status. So we're either setting something about like the baud rate or something about it, about the chip, something about the control and status. Do we have a byte, not have a byte, you know? And that kind of brings us to then those port commands like out or like in. So IORQ low to enable the chip. So when IORQ is low, it goes through an inverter which pulls it high, which enables the chip. And we know from the previous screen that when an IORQ is low, it's active low. That means it indicates that the lower half of the address bus holds a valid IO address. That's why we need to turn on this chip, because we know that there's going to be a port call somewhere on these addresses. Is going to be a call to a specific port IO, and it could be ours. It could also be another device, right? You can have multiples. If it's the lower 8 bits of the address bus, that would give us 256 address ports, right? Okay. So, and then last but not least, we have the write. So if it's a write, it goes to a read. That's interesting. So if write goes high, read goes high. But remember that write is active low. So if we're doing a write, we know we're not doing a read. If that makes any sense to you. It can be a little confusing, and that's why I kind of wrote this out so you could see it. If we set these proper bits, except for this one, remember A0 controls the register select. We can see, doing a little bit of math, that we're talking about hex port 80 for control and hex port 81 for data access. So when an in instruction or an out instruction happens and it references port 81, it's going to do some kind of data access, either writing data or reading data. If it references port 80, hex 80, then it's going to be a control instruction. So let's go down. I looked at the source code for the Microsoft Basic that we're going to run. And inside there, sure enough, I found the references to our ports. Now, they had to be in there because when we boot that ROM and it starts working, it's going to, remember, it's going to display something on the screen about what Microsoft Basic version it is. It's going to probably put a cursor there so we can start typing in an instruction. As we type an instruction, interrupts need to fire so that it knows, hey, I got data on the bus waiting to be picked up. So then it starts reading it in to figure out what basic command we're typing. And in fact, that's pretty much exactly what's going on. There's both some interrupts set, a loop going on, and it's processing all this data. We'll look at the basic code later for Microsoft Basic. But what we're trying to do is we're trying to understand, how does this serial board work? And if you look, this is actually cut and pasted from the source code for that original version of Microsoft Basic that's been modified specifically because our computer, our RC2014 Classic II, talks on these ports. If I had designed the computer, let's say, the architecture, or you had designed it, you might have put that serial I/O port someplace else, because it's all simply controlled by the decisions that were made of which lines to use. We could have used other lines. We could have put different logic in here. But this is what the designer of our Classic II decided to do, which meant somebody had to go and modify this version of BASIC, because this version of BASIC was created like late 70s, I think. And obviously this computer didn't exist then. Of course, the gentleman who designed this computer that we're building, the Classic II, his name is Spencer Owen, and I'm hoping to have an interview with him in the future for you guys to see. Maybe he knew a lot about computers at the time and knew that this was the port on numerous other Z80s. That could have been something, a decision that he made. But I happen to know in this case that the code was modified so that it would support these addresses. So you can see here, I'm going to read something in. So it uses our data address, right? And we're going to read in. This is us sending out. We're going to write something out to it. So yeah, so that's pretty much how this goes. I will put up all of the, I'll put out this handout. I'll put up some links to the other handout that I've seen, which has a lot of good information in it. And that should help you kind of figure out what's going on. All right, so with that, I appreciate everything. Remember to like and subscribe. Also learn something new every day, and stay tuned for the next PCB build, which I believe is the RAM, I think, is next. All right, guys, take it easy. Thank you very much. Bye.